time complexity. But this is a good question. It's like, how really is time complexity related to space complexity? Those two concepts are in the runtime. So, like it says, it's under the umbrella of space, and time complexity is under the umbrella of runtime. But actually, how is time complexity directly related to the space complexity? Because we know that space is a physical concept. So but the time is related to the instructions that have to be processed within that space. So, are we talking about a certain memory limitation that is constrained, and the formulas have to operate inside that constraint, that space constraint? So, I think that to understand big O, I should understand how the time complexity is directly related to the space complexity, the physical constraints. In fact, I would argue trying to figure out the big O, or the time complexity of the code, really helps to understand the code itself. And if you can do that, you can probably understand more how to write code for different problem-solving situations involving those types of, time complexities. You'd already know what the time complexity is, and you'd be used to writing code for that time complexity. So here I'm trying to use ChatGPT to explain the example, but I still don't really understand it, but I keep using it. So I thought factorial took the most time, but actually it says O of small n. I don't even know if that's the same as O of big N. Do we have an O of big N? It's just O of n. That's an O of big N, O of small n. So check this out on the graph. Time complexity curves. So this one should be the factorial of factorial, which takes the most time. And that's what I thought, factorial takes the most time. So I'm going to double check that on the internet. I saw a lot of notations that I wasn't able to match, so in that case, it's better to stay with one source, the same source of information. So I was just looking at this example. This was a divide by 2, example 16. And so it was a log problem, O log n, and wasn't so obvious it was O log n here, but when they said that, it was when they got to this part, the number of times we can divide by 50 or by or n by 2 until we get down to the base. So when they said that, then I knew it was an O log n problem. And that's what they said here. As we discussed, the number of times we can have n until we get 1 is O log n. So I mean, these the patterns, there are only certain so many patterns. So that's one pattern, is the O log n divided by 2 O log n. And so if I get a little better and I recognize that this code here is an O log n, or is a divide by 2 problem, the reason why that threw me off also is I saw the n over 2 here, but the result here is then something, I don't know what this is, multiplied, or is this exponent. This operation here was applied for the return of this variable current CU curve. So I thought that was multiplying again. I didn't think it was going like the last result was division by 2. So, but it is. So, and this is Java code also. So, I could read it, but a little. But yeah, it's an O log n, and understanding the big O actually helps me also, like, really understand this code So I'm not still not at the point where I can just have a problem and then write the code um, yet, but I am at the state where I know there's only a certain number of patterns and limited number of patterns, and this is one of them. And yeah, just keep moving on that way. So I think I'm officially 10% finished with this book, Cracking the Interview, which is very nice, very cool. And I'll just continue from here. I think that actually concludes the Big O. I understand a little more, but the Big O definitely helped me understand the algorithms and the code more. So will definitely be feature point on that, and we'll get back to that later. Now I am at technical questions. Yeah, so here's good advice. It says that we're usually only expected to know the basics for the data structures and algorithms. So it's definitely good right there. Like those that are not from computer science, said that it's easy after you know what you're supposed to know. And like they say, if they can do it, then anyone can do it. Data structures, linked lists, trees, tries, and graphs, stacks and queues, heaps, vectors, array lists, hash tables, algorithms, BFS, DFS, breadth first search, depth first search, binary search, merge sort, quick sort, the two sorts, and the two first searches, which is what I call it, the two FSs and the two sorts. Concepts, bit manipulation, memory stack versus heap, recursion, dynamic programming, big O, time and space. So these concepts are very nice to know that, but this is really the meat right here. This algorithms, I think this is really where the shit hits the fan. So we've got 5 algorithms, and 2 are sorts and 2 are FSs for searches, and then 1 binary search. So these 5 right here, I can count them on one hand. Just know what they do and that they are made of these data structures. So this is really the core right here. If we can have a lot of control over this part, then that would be really good. So the breadth first search is bit manipulation. Depth first search is, but I'm not sure if these are correlated. So let's read more. So here now it's starting to talk about the space complexity. Not sure if, well, I'm starting to talk about memory use. So I'm not sure if that's space complexity. Yeah, so it just said brute force again. Listen, example, brute force. So designing here. Listen, pay very close attention to the information in the problem description. Probably need it all for an you probably need it all for an optimal algorithm. Then most examples are too small or are special cases. Debug your example. Is there any way to special case? Is it big enough? Then brute force. Get a brute force solution as soon as possible. Don't worry about developing an efficient algorithm. State a naive algorithm and its runtime. Then optimize from there. Don't code yet those. So what's brute force? I have not seen this as an algorithm yet, so I think what it's meaning is just design something that works, whatever it is, and then optimize it from there. Go to the optimize step. Walk through your brute force with view de-optimization, or try some of these ideas. Look for any unused info. Usually need all the information in a problem. Solve it manually on example. Then reverse engineer your thought process. Solve it incorrectly and then think about why the algorithm fails. Can you fix those issues? They'll make a time versus space trade-off. Hash tables are especially useful. So hash tables are dictionaries, and so it's talking about time and space. The time-space complexity trade-off, the BUD, bottlenecks, unnecessary work, and duplicated work. Think about that to minimize the time-space complexity. How else to optimize? So look for unused info. Then the walkthrough. Now that we think we have an optimal solution, walk through your approach in detail. Make sure you understand each detail before you start coding. 6, implement your goals to write beautiful code. Modularize your code from the beginning and refactor to clean up anything that isn't beautiful. So what is the most important part here is like the brute force. So the first state is to get to a brute force situation, and once we have something that's like working really roughly, however it did, we want to go through the optimize section. So we've got it working simply, but the optimize will take care of every thing that was missed. Then after that, we walk through it in detail so to make sure I understand each detail before starting the coding. Okay, so this is even at this step, the coding is not, I haven't done any coding. So this is all design on paper before I've coded anything. And then 6, implement, write beautiful code, modularize the code from the beginning and refactor to clean up anything that isn't beautiful. So modularize and refactor. This is like using object-oriented programming and writing the classes and objects, the OOP, and then after something is written, then refactoring it. And then test. So 7, test in this order: conceptual test, walk through your code like you would for a detailed code review, unusual or non-standard code, hotspots like arithmetic or null nodes, small test cases. It's much faster than a big test case and just as effective. Special cases and edge cases, and when you find bugs, fix them carefully. So what were the points here? I think the points that stood out to me was the brute force design, then and then the it kind of starts here: brute force, optimize, details, write into code, or we can say brute force, optimize, and then write into code, and then test is looking for little details like bugs that happen after the code is written, and walkthrough are the details that are looked for after the optimization, after some attempt to clean up the brute force. So what I'm going to look for in the future in this book is how to write the brute force. So for brute force examples, I might even search for that right now. And I got quite a few examples for brute force, explaining brute force, so I can go to the first step and get an idea, the first mention, and start reviewing that and get an idea of what it means by brute force. So going back to the beginning of the book, about the interviewer, how the interviewer is thinking. These lines, for example: if they get nervous and stuck and aren't sure where to go, suggest to them that they walk through the brute force solution and look for areas to optimize. So we just saw those steps, right? Step 3 and 4, I think it is. If they haven't said anything and there's a fairly obvious brute force, remind them that they can start off with a brute force. The first solution doesn't have to be perfect.